This presentation is delivered by the Stanford Center for Professional Development.
Hey there! Oh, we're back, and now we're getting down and dirty. We're going to do more pointers and linked lists and implementation. This is actually going to be our life for like the next week and a half, is just even more implementation, trying to think about how those things work on the backside. So I will do another alternate implementation of the stack today. So we did one based on vector. I'm going to do one based on a linked list. And then I'm going to do a cube based on linked list as well, to kind of just mix and match a little bit. And then we're going to start the editor buffer case study, which is the material that's covered in Chapter 9. I probably won't get through all of that today. What we don't finish today, we'll be talking about on Friday. And then we'll go on to start talking about map implementation and look at binary search trees. How many people started priority queue? How many people got somewhere feeling good? Not just yet. One thing I will tell you is that there are two implementations you're working on, and I listed them in the order of the one that the material we've seen the most, right? We've talked about linked lists more than we have talked about things that are tree and heap based. So I listed that one first, but in fact, actually, in terms of difficulty of coding, I think the second one is a little bit more tractable than the first. So there's no reason you can't do them in either order if it feels good to you to start on the second one before you come back to the first one, or just trade off between working on them. If maybe one of them's giving you some fits, just look at the other one to clear your head. So just a thought about how to approach it. Okay, so I am going to do some coding. I'm going to come back to my slides in a little bit here. But to pick up where we left off last time, was we had written a vector-based implementation of the stack abstraction. And so looking at the main operations here for a stack are push and pop, right? That its mechanism here is just to add to the end of the vector that we've got. So letting the vector handle all the growing and resizing and memory manipulations that are needed for that. And then when asked to pop one, we just take the one that was last most added, which will be at the far end of the array. And so given the way vector behaves, knowing that we know it's a contiguous array-based backing behind it, then we're getting this O of 1 access to that last element to either add a new one down there or to retrieve one and remove it from the end. So the push and pop operations both being constant time, no matter how many elements are in the stack, 10, 15, 6 million, the little bit of work we're doing is affecting only the far end of the array and not causing the rest of the contiguous storage to have to be jostled whatsoever. So pretty easy to get up and running. So in general, once you have one abstraction, you can start leveraging it into building other abstractions, and the vector manages a lot of the things that any array-based implementation would need. So rather than using a raw array, there's very little reason to kind of, ditch vector and go to straight raw array in this case, because all it basically does is open up opportunities for error and kind of management, and the kind of efficiency you can gain back by removing vectors intermediate stuff is really not very profound, so not worth probably taking on. What I'm going to do is consider, though, a linked list implementation. We had talked about a linked list for the vector, and we kind of discarded it as likely to not lead anywhere interesting. I actually am going to fully pursue it for the stack, though, because it actually turns out a linked list is a good fit for what the behavior that a stack needs in terms of the manipulations and flexibility. So if I have a stack of integers where I've pushed 10, 20, and 30, I'm going to do that same diagram we did for the vector one, what I did for the stack, is that one possibility is that I put them in the list in this order. Another possibility is that I put them in this order. We'll call this strategy A, we'll call this strategy B. They seem, fairly symmetric, right? Is there going to be a strong reason that leads us to prefer strategy A over B, or are they just equally easy to make get the things done that we need to do? Anybody want to make an argument for me? Help me out.
Last in, first out.
Last in, first out.
So A is better because we have to find it.
Be careful here. So 10, 20, 30 means that the way the stack looks is like this. 10, 20, 30. And so it's the access to the top that we're interested in, right? Mm-hmm. That the top is where activity is taking place. Oh. So we want to be adding things and removing things from the top. So do we want to put the top at the end of our list or the front of our list? Which is the easier to access in the linked list design? The front, right? So in the array form, right, we preferred this, putting the top kind of at the far end, because then that only involved the jostling of that. that having immediate access to the top here in the front is actually going to be the better way to get the linked list strategy working. Let me actually go through both the push and the pop, though, to convince you of why this is true. So if I have access in the 10, 20, 30 case, I can actually keep a separate additional pointer, one to the front and one to the back. So I could actually be kind of maintaining at all times this pointer to the back. If I did that, right, then a subsequent push of a 40 is pretty easy to tack on a 40. So it turns out it would be that the adding, it's the push operation that actually isn't really a problem on this on strategy A. We can still kind of easily and over one at a time, if we have that tail pointer, just tack one onto the end. It has to do on the pop operation, where if I need to pop that 30, I need to adjust that tail pointer and move it back a cell. And that's where we start to get into trouble. If I have a pointer to the tail cell, there is no mechanism in the singly linked list to back up. That if I say, oh, it's time to pop 30, then I would actually need to delete the 30, get the value out, but then I need to update this tail pointer to point to 20, and 30 doesn't know where 20 is. 30 is oblivious about these things. And so the only way to find 20 in a singly linked list would be go back to the very beginning, walk your way down, and find the one that pointed to the cell you just took out of the list. And that's going to be an operation we want to avoid. In the strategy B case, right, adding a new cell basically means putting a 40 in is allocating a new cell and then attaching it, splicing it in, right, which means wiring in two pointers, something we can do easily in constant time. And then popping one is taking that frontmost cell off. So easy to get to, easy to update and kind of splice out. So no traversal, no extra pointers needed. The idea that there are 100 or 1,000 elements following the one that's on top is irrelevant. It doesn't have any impact whatsoever on the running time to access the front or stuff a new element on the front, take an element off the front. So it is strategy B that gives us the best setup when you're implementing a stack as a linked list. So let me go ahead and do it. I think it's kind of good to kind of just see, like, oh, what's it like to just write code and make stuff work? And so I'm kind of fond of this, and you can tell me. I make a cell T. It has an elem type value, and it has a cell T next. That's there. And then I have a pointer to the frontmost cell. So in addition, it might be that in order to make something like size operate efficiently, I might also want to cache a number of cells that I would update as I add and remove. I can also decide to just leave it out for now. Maybe I'll actually even change this to be the easier function to write, which is the isEmpty form. And that way I don't even have to go down that road for now. So I go back over here to this side, and I got to make everything now consistent with what's going on there. Okay. Let's start off with our constructor. Always a good place to make sure that you get into a valid state. In this case, we're going to use the empty list, so the head pointer pointing to null to tell us that we have no cells whatsoever in the list. So we don't pre-allocate anything, we don't get ready. The linked list has kind of the nice convenience of being able to allocate on demand each individual cell that's asked to be added to the list. The delete operation actually does really need to do some work. I'm actually not going to implement it, but I'm going to mention here that I would need to delete the entire list, which would involve iterating or recursing my way down to kind of do all the work. And then I changed this from size to isEmpty. I'd like to know if my list is empty, then I can just test for head is equal to null. So if it's null, then we have no elms. Let me work on push before I work on pop. I'll turn them around. So push. The push operation is make myself a new cell. All right, let's go through the steps for that. New cell equals new cell T. New piece of memory out in the heap, the size to hold, a value, and a next link. I'm going to set the new cell's val to be the parameter that came in. And now I'm going to splice this guy onto the front of my list. So the outgoing pointer I'm doing first, the new cell is allocated and leads to what was previously the frontmost cell. And then the head is now updated to point to this one. Two pointers wired, one value assigned, and we've got a new cell on the front. The inverse of that, taking something off of my list, I'm going to need to kind of detach that frontmost cell, delete its memory, get its value, things like that. So the error checking is still the same at the very beginning. Like if I've got an empty stack, I want to be sure that I don't just kind of dereference null and get into some bad situations. So I report that error back using error, which will halt the program and stuff. Otherwise, right, The element that's on top is the one that's the value field of the head cell. So knowing that head is non-null, that's a safety reference to do there. And then I'm going to go ahead and get a hold of what that thing is. And I'm going to update the head to point to the cell after it, so splicing it out, and then deleting the old cell. So just taking a look at these, right, like there's definitely, once we start doing pointers, right, there's just opportunities for error. I feel kind of good about what I did here, but I am going to just do a little bit of tracing to kind of confirm for myself that the most likely situations that get you into trouble with linked lists is you'll handle the mainstream case, but somehow forget one of the edge cases, such as what if the list was totally empty or had just a single cell? Is there some special case handling that needs to be dealt with? So if I think about it in terms of the push case, you know, I might say, well, if there's an existing set of cells, so we're using strategy B here. Let me erase A so we're not even looking at it. That if head is currently pointing to a set of cells, right, then my allocation of a new cell out here, right, assigning its value, assigning its next field to be where head points to, and then setting head to this new guy looks to be good. If I also do that tracing on, well, what if the list that we were looking at was just null to begin with? So there was no cells in there. This is the very first cell. Is it going to have any trouble kind of stumbling over this case? So it would allocate that new cell 40, assign its value, set the next field of this to be what head is. So that basically just sets the trail coming out of 40 to be null, and then updates the head to there. So we've produced a singleton list, right, with one cell. Okay, so that looks like we're doing okay on the push behaviors. The pop behavior, same sort of cases may be relevant to think about. Okay, if it's totally empty, right? If we come in and we've got, you know, an empty cell, then the isEmpty test should cause it to error and not get down to the rest of the code. Let's say that B points to some, you know, sequence of things, 30, 20, 10. That taking the head value off and kind of writing it down somewhere, saying, okay, 30 was the top value. The old cell is currently the head, so we're keeping a temporary on this thing. And then head equals head arrow next, which splices out the cell around. So we no longer have a pointer into this 30. The only place we can get back to it is with this temporary variable we've assigned here of old. And then we delete that old to reclaim that storage. And then our list now is the values 20 and 10, which followed it later in the list. We can also do a little check that says, well, what if it was the very last cell in the list that we're trying to pop? Does that have any special handling that we have overlooked? If I have just a 10 here with a null after it, I'll go through the process of writing down the 10, assigning old to where head is, then assigning head to head arrow next. Well, head arrow next field is null. So we stop pointing to that and we set our list to null, and then we delete the cell. And so after we're done, right, we have an empty list again, the head pointer back to null. So it seems like we're doing a pretty good job. Have a bunch of cells, have one cell, no cells, different things kind of seem to be going through here doing the right thing. Let's test it. A little bit of code on this side. Pushes and pops and does a few things. Look at that pop empty stack. What have I got there? Oh, I think I may have code that, oh, it deliberately makes that error, in fact. That was designed to test our handling on that. So let me put these in, and I'll say while not s dot empty, pop to the end. So let's see if we get back a 3, 2, 1 out of this guy. Okay. So we managed to do okay, even on feet of that. So looking at this piece of code, right, the two operations we're most interested in, both being push and pop, right, are each O of 1, right? The idea of the number of elements out there, right, are not changing anything about its performance, right? It does a little bit of machination, a little bit of pointer rearrangement up here at the front or the end. And so it has a very nice tight allocation strategy too, which is appealing relative to what the vector-based strategy was doing. Was like, well, allocating things in advance on our behalf, extending our capacity. That every now and then we had some little glitch, right, when you were doing that big resize operation that happened infrequently. You won't have that same concern with this one, right? It does exactly what it needs at any given time, which is allocate a single cell, deletes a single cell, so keeping the allocation kind of very tidy in that way. So they'll both end up being of1, and both of these are commonly used viable strategies for how a stack is implemented, right? Depending on the, just inclination of the programmer, right? They may have decided that one was the way to go versus another, that you will see both used in common practice because there really isn't one of them that's obviously better or obviously worse, right? This uses a little bit more memory per cell, but then has no excess capacity in it. The vector has a little excess capacity, but no overhead per cell. There's a few other things to kind of think about trading off in terms of the code itself is a little harder to write if you're using a linked list, is the truth. That means it's a little bit more error prone, and more likely you'll make a mistake and have to debug your way through it in a way that the vector was pretty easy to get right without a lot of tearing out your hair. Okay. Now, if we can do stack and queue that fast, stack that fast, then you figure queue must be not so crazy either. Let me draw you a picture of queues. Okay, got my queue, and I'm going to use the enqueue operation on it to put in a 10, to put in a 20, to put in a 30. And then I'm going to try to get back out what was frontmost. Okay, so queue is FIFO, first in, first out. Your waiting line, right, whoever's been in the queue longest is the first one to come out. Very fair handling of things. And so if we were to think about this in terms of, let's go straight across the linked list. We just got our head around the linked list for the stack. Let's see, does linked list for a queue provide the same kind of easy access to the things we need to do the work? So it seems like the two strategies that we looked at for stack are probably the same two to look at for this one, right? Which is we go in the front ways order, so having the very front of the queue accessible in there, and then traversing our way down to the tail, or the other way around, right? Having the tail of the queue up here in the front, leading away to the head of the queue. So this is head. Well, I'll call this front of queue, and this is back. This is the back. This is the front. Okay, strategy A, strategy B. So first off, ask yourself, where does the queue do its work? Does it do it at the front, or does it do it at the back? It does it at both. That when you're enqueuing, right, you are manipulating the back of the queue, adding something to the tail end of the line. When you are dequeuing, you're accessing the front of the queue. So unlike the stack, where both the actions were happening in the same place, and that kind of unified your thinking about where to allow for that easy access to the top, the one thing that the stack cared about. The bottom of the stack, right, was buried and it didn't matter. The queue actually needs access to both. So that sort of sounds like that both these strategies, right, like have the potential to be trouble for us, because it's like in the linked list form, right, the idea that access to the head is easy, access to the tail, right, is a little bit more tricky. Now I said we could add a tail pointer, and maybe that's actually going to be part of the answer to this, right, that is, as it is with no tail pointers in here, that adding an item to A would involve traversing that queue to find the end to put a new one on. Similarly, if in B, the inverse operation here that's going to be our trouble, which is dequeuing, would have to kind of walk its way down to find the lastmost element in the linked list ordering, which is the front of the queue. So let's say we add a tail pointer in both cases. So we have a head that points to here and a tail that points to there. It's like, will that make our problem a little bit easier to deal with? So let me look at B first. That adding to the back of the queue is easy. We saw how we did that with the stack, right? So that the enqueue operation doesn't need that tail pointer, and it already kind of wasn't a problem for us. Now the dequeue operation would mean, okay, using our tail pointer to know where the lastmost value is tells us it's 10, but we have the same problem I had pointed out with the stack, which is we can get to this value, we can return this value, we can delete this cell, but what we need to do that also in that operation is update our tail pointer so a subsequent dequeue can do its work efficiently. And it's that backing up of the tail pointer that is the sticky point. That given that 10 doesn't know who points into it, the singly linked list is very asymmetric in that way, that you only know what follows you, not what precedes, that backing up this pointer is not easy. It involves a traversal, going back to the beginning, walking your way down to find somebody who points to the last cell. So it seems like this tail pointer didn't buy us a lot. It helped a little bit, to get some of the operation up and running, but in the end, keeping and maintaining that tail pointer sort of came back to bite us. In the case of the strategy A, the tail pointer gives us immediate access to the back, which we're going to need for the NQ. So if I go to NQ of 40 in this case, then what I'm going to need to do is make a new cell, attach it off of the current tail cell, and then update the tail, right, to point to that cell. Well, that update's moving forward down the list, right? If you're on the third cell and you add a fourth cell, you need to move the tail from the third to the fourth. Well, moving that direction is easy. It's the backing up where we got into trouble. So in fact, this suggests that strategy A is the one that we can make both these operations manipulate in constant time in a way that this one got us into trouble. Let's see if we can do it. We switch over. I've got an empty my queue here. Maybe I'll give it also an is empty instead of a size, because it has the same problem with size, which is either you have to go count them or you have to cache the size. So I will build the exact same structure, in fact. Cell type val, cell type next. So this one's going to have both a head and a tail pointer, so we keep track of the two ends we got going. I think I am missing my queue.cpp here. Okay. Now let's flip over. Okay. And then I will make the same comment here about, you need to delete all cells. So I set the head and the tail to null. That'll be my empty state that tells me that I've got nothing in the queue, nothing at all so far. And my is empty will check that, return the head equals null, just like it did. So in fact, it looks a lot like the stack, actually. And here I'm going to show you something actually kind of funny. If I go take my stack.cpp's pop. So if you remember what pop did over here was it took the frontmost cell off the list. And in the case of the queue, that was the popping operation. It turns out the dequeue operation is exactly the same. If we're empty, right, then we want to raise an error. Otherwise, we take the head's value. We move around the head. We delete the old member in the turn. So it's not actually the top element. I could actually, if I were being a little bit more careful about my copy and pasting here, I could really call that front. It is the frontmost element, not really the top. But in fact, the exact same mechanics work to take a cell off the front in that way. Well, that's sort of nice. And then it's like, since I have some code around, I might as well try it. My stack also kind of does some things useful in push that I might be able to use. It's not exactly the same because it's adding to the front, but it is setting up a new cell. So I make a new cell, and I set its value. And then its attaching looks a little different. All right, so let's take a look at what we got to do here. We made a new cell, copied the value in. Now the goal is, given our pointer to the tail, we want it to attach onto the tail. So we know that it's always going to have a next of null, the new cell. So no matter what, it will be the new lastmost cell, and it definitely needs that sentinel value that tells us we're at the end of the list. And then we have to attach it to our tail. And I'm going to write this code first, and it's going to be wrong, so just go along with me in this case. Is the tail's next is the new cell. So that's kind of wiring in the pointer from the tail onto the cell we have there. And then we want to update the tail to point to this cell. So almost, but not quite everything I need to do. Somebody want to point out for me what it is I have failed to consider in this situation? If the what?
Empty.
Yeah.
Trying to make null point to something.
Exactly. So if my queue is totally empty, so in these cases, right, one thing you can often think about is whenever you see yourself with this arrow and you're dereferencing something, you have to consider, well, is there a possibility that that value is null? And if so, I better do something to protect against it. So in the case of the new cell here, I'm setting its value next. I just created that cell. We know it's valid. It's out in the heap. We've got good memory. And so that part's good. But this access to the tails next is assuming that there is a tail, that there is at least one cell already in the queue that the tail is pointing to. When that's not true, this is going to blow up. It's going to try to dereference null. So what we can do here is we can just check for that. We can say, well, if the queue is empty, then what we want to do is say that head equals tail equals new cell. What we just created. Otherwise, right, we've got some existing tail, and we just need to attach onto it. So this is what I meant about the idea that often there are a little bit of special cases for certain different inputs. In particular, the most common ones are an empty list or a singleton list being distinguished from a list that has 2 or more elements. So sometimes it's all about, a singleton list is a little problem. Sometimes it's the empty list. In this case, it's exactly the empty list. Like a single cell is actually fine. 1, 10, 6,000 all work equally well. It's that single, the empty case that we have to do a little bit of special work on, setting our head and tail to that new thing that came in. So with this in play, I'm going to go back to my client use of this. I'm going to stop talking about my stack, and I'm going to change it into my queue. End queuing instead of pushing. And dequeuing instead of popping. And with any luck, 591 errors. Well, that's really, 591. What's that about? Who really minds that? Can we see our errors? How about you show me your errors? Oh, yeah, this is the error that I was, we had talked about, and then of course I have failed to do. I made my pound of fun. So this is the kind of thing that you'll get from failing to protect your pound include from being revisited. And so if I haven't defed this funny little symbol I just made up, then I went through and defined it, and at the bottom I had an ndef. And so if it came back around and it saw this same header file, it was supposed to say, I've already seen that symbol and I won't do it. But in fact, I had accidentally named one of them with a capital H and one with a lowercase h that says, if this symbol's not been defined, then define this other symbol and keep going. And so the next time it saw the header file, it says, well, if this lowercase h symbol hasn't been defined, well, it hadn't, right? And so it went and made it again, and then it kept doing that until it got really totally twisted up about it. So I will make them match with any luck without the caps lock key on 3 times as a charm. And then 1, 2, 3, pop out the other side of my queue as I was hoping. There we go. Okay. So you know what I'm going to do actually is I'm actually not going to go through the alternate implementation of queue, but I'm just saying that given that it works so well for stack, right, to have this kind of single linked list, efficient allocation, it's not surprising that queue, right, and what this is to remind us about, when I had said earlier, I said, well, you can do things with vector, you can do things with stack, or anything you do with stack or queue, you could do with vector if you were just being careful, right? The pushing and popping in and queue dequeue are operations that you could express in other terms of vector adds and removes and inserts and things. But one of the nice things about providing an abstraction like a stack or a queue that says these are the only things you're allowed to do, add at this end, remove from that end, it gives you options as an implementer that don't make sense for the general purpose case. That the vector as a linked list had some compromises that probably weren't worth making. But in the case of stack and queue, it actually came out very cleanly and very nicely, like this tidy little access to one end or the other end or both, right, was easily managed with a linked list, and then it didn't have any of the constraints of the contiguous memory to fight with. And so often, right, the idea that having a data structure that actually offers less gives you some different options as an implementer, because you don't have to support access into the middle in any efficient way, because the stack and queue don't let you do that. They don't let you rifle through the middle of the stack or the queue to do things. And that gives you some freedom as an implementer, which is neat to take advantage of. Question?
Should we feel like we did in Java that, we were supposed to use an array whenever we could, because an array list uses more memory, for example. So, does a queue and stack, do they use relatively more memory than an array, for example?
So typically, right, they'll be about the same because of exactly this one thing, which is it allocates tightly, so it allocates one cell per entry that's in there, right? And that cell has this overhead in the form of this extra pointer, right? So in effect, it means that everything got a little bit bigger because everything's carrying a little overhead. Okay, so there's a little bit of that. The thing that the array is doing is it tends to be allocating extra slots that aren't being used. So it's not usually tightly allocated either. So in any given situation, it could be as much as twice as big because it had that extra space. So kind of in that trade-off, right, they tend to be in the same general range. This one has about twice the space for a thing that's 4 bytes. It has a 4-byte pointer. If the thing's much bigger, then it turns out actually this 4-byte pointer might be a smaller percentage of the overhead and would be a larger amount of the capacity in the excess case. So for a lot of things, they're going to be about the same range, and then there's a few isolated situations where, yeah, if you have very big things being stored, having a lot of excess capacity is likely to be a more expensive part of the vector strategy than the linked list. But the linked list does have this kind of built-in overhead for every element. And so it's not the case that I think you would say, like right off the bat, well, definitely array over linked list because of the allocation space. It's like, you'd have to think about the whole picture. I mean, that's maybe the whole lesson of the next couple lectures is going to be like, well, you know what, it's about trade-offs. It's not that one strategy is always going to be the clearly better one. If it is, then there will be no reason to think about anything else. It's like, oh, there are times when you know that one is just great and there's no reason to think about anything else, and then there's lots of other times when there are reasons to think about different ways to solve the same problem. So let me propose a case study that has some neat things along the way, but you're going to have to willingly suspend disbelief on this being relevant at first, because it's going to seem like you've been transported back to 1970. And which was a very bad year, long before you were born. The idea is we're going to think about the idea of a text editor. So Microsoft Word, or your email send window, or BBEdit or Xcode. All of these things, right, need to have some backing of what is traditionally called a buffer. A buffer. It's kind of a funny word, right? But a buffer of characters behind it. Okay. And that buffer is used as the kind of document storage for all the characters that are in, that you're editing and you're moving around. So as you kind of bop around and you move around, there's some insertion point, often called the cursor, where you type, characters appear, and characters get moved as you insert. You can select things and delete them and cut, copy, and paste and all that sort of stuff. So like, what does that data structure look like? What is the kind of thing that wants to back a buffer? What kind of things, right, are important in that context to be able to support, and what operations need to be optimized for that tool to feel facile. So what we're going to look at is a real simplification, kind of taking that problem, kind of distilling it down to its essence, and looking at just 6 operations that kind of are at the core of any text editor, about moving the cursor forward and backwards with these commands, jumping to the front and the back of the entire buffer, and then inserting and deleting in relative to the cursor within that buffer. And we're going to do this with this just extremely old school interface that's actually command line based. It's like VI comes back from the dead, for those of you who have ever heard of such things as VI and Emacs. And so we're going to look at this because actually there's a lot of interesting ways you can approach that that take advantage of some of the things we've already built, like the vector and stacking queue and the linked list, and sort of think about, well, what kind of options play out well. So what I'm going to show you first off is just what the tool looks like, so you can really feel schooled in the old way of doing things. So I insert the characters A, B, C, D, E, F, G into the editor, and then I can use the command B to back up. I can use command J to jump to the beginning, E to jump to the end, and so F and B moving me backwards, F moving me forwards, and then once I'm at a place, so let's say I jump to the end, I can insert Z, Y, X here at the beginning, and it'll slide things over, and then I can delete characters, shuffling things down. So that's what we've got. Try to imagine now that's like, okay, building Microsoft Word on top of this. There's a lot of stuff that goes, between here and there, but it does give you the idea that kind of the core data structure requirements, every word processor needs some tool like this, some abstraction underneath it to manage the character data. So, okay. Where do we start? Where do we start? Anybody want to propose an implementation? What's the easiest thing to do?
An array with all your characters.
Yeah, an array, something like that. Like, and if you think array, you should actually immediately think after it, no, I don't want to deal with array. I want a vector. I'd like a vector. Vector, please. Right? So I'm going to show you what the interface looks like here, that we have like buffer and then these 6 operations. We're going to think about what the private part looks like. And we say, what about vector? Vector handles big, chunky things indexed by slots. that might be a good idea. So if I had the buffer contents A, B, C, D, E, right, and if I could slam those into a vector, and then I would need one other little bit of information here, which is, well, where is the cursor at any given point? Because the cursor is actually where the insert and delete operations take place relative to the cursor. The buffer is also going to manage that, knowing where the insertion point is, and then deleting and inserting relative to that. So I could say, okay, well, I'll need some index. The cursor actually is between two character positions. That it is, this is like slot 0, 1, and 2. And so the cursor is between actually 1 and 2. And there's just a little minor detail to kind of have worked out before we start trying to write this code, which is, do we want the cursor to hold the index of the character that's to the left of it or to the right of it? It's totally symmetric, right? If I have these 5 characters, it could be that my cursor then goes from 0 to 4. It could be that it goes from 0 to 5, or it could be it goes from -1 to 4, depending on which way I'm doing it. I'm going to happen to use the one that does 0 to 5, so where it's actually recorded as the character after it. Okay, so that's just kind of the starting point, and I'm going to write some code and make it happen. Go back to Xcode, and so I'm going to remove this. Didn't reference it. It's okay. And then I'm going to add the things I want to replace it with. So I want to put in the editor code and to put in the buffer code. Is buffer already in here? Why is buffer not letting me do that? Maybe buffer's already here. Okay. All right. So let's take a look. Get my buffer. So right now, let's take a look at what's in buffer.h. I think I have just the starting set of information. So it has the move cursor, move the cursor around, has the delete, and it has. Let me make it have a set of variables that I want. I got my cursor, I got my vector of characters. Right now it has disallow copying, I think just because in anticipation of going places where disallow copying is going to be required. Right now, because it's using vector and vector has deep copying behavior, I'm actually okay if I let member-wise copying go through, but I'm actually going to not do that right away. All right, so then let's look at the implementation side of this. And I have an implementation in here I want to get rid of. Sorry about this, but I left the old one in here. Okay. That will do all the things that need to get done. Okay, so let's do with, at the beginning, kind of starting off, right, we will set the cursor to 0. So that's the vector gets started, initialized empty, nothing else I need to do with a vector of characters, but I do need to set the cursor position of that. And then moving the cursor position forward is mostly just doing this, right? Cursor ++, right? It's just an easy index to move it down. But I do need to make sure that the cursor isn't already at the end. So if the cursor is less than the size of the vector, then I will let it advance. But it never gets beyond the size itself. So like all of these are going to have the same problems, like, oh, if I'm already at the end and somebody asks me to advance, I don't want to suddenly get my cursor into some whack state that's sort of back that. Similarly on this one, right, if the cursor is greater than 0, right, then we can back it up. Moving the cursor around. Moving the cursor to start is very easy. Moving the cursor to the end is also very easy, right? We have a convention about what it is. And so then inserting a character is also pretty easy because all the hard work is done by the vector, where I say insert this new character at the cursor position, right, this character, and then advance the cursor to kind of be past it, and then deleting the character also. Pretty easy. Let me show you, actually, before I go finishing the code, I just want to show you this little diagram of what's happening while I'm doing stuff. So this is kind of a visualization of the things that are happening. So this is showing the vector and its length, and then the cursor position as we've done things. So I've inserted 6 characters. The cursor is currently sitting at the end, and so the length and the cursor are actually the same value right now. If I issue a back command, right, that decrements the cursor by 1. I issue another one, it backs up by 1. And then eventually the cursor gets to position 0, and subsequent backs don't do anything to it, right? It just kind of bounces off the edge. Moving forward, same sort of deal. It will advance until it gets to the length, the size of that text, but won't go any further. And that jumping to the front and the end are just a matter of updating that cursor position from 0 to the size and whatnot. The operation where things get a little more bogged down is on this insert, where I need to insert at this position, so I insert the X, Y, Z into the middle there, and you can see it kind of chopping those characters down, making that space to insert those things in the middle. Similarly, doing delete operations, so if I jump to the beginning and I start doing deletes here, it has to copy all those characters over and decrement that length, right? That the vector is doing that work for us on remove at. That means that if the buffer is very large, which is not atypical in a word processor situation, you can have your PhD thesis, right, which has hundreds of pages. If you go back to the beginning and you start deleting characters, you'd hate to think that it was taking this massive shuffle time to get the work done. So let's see if my, and then I'm going to comment out, bring in the display that, oops, didn't like something here. Multiple build commands. Well, that's really very helpful. I'm going to ignore that for now. All right, now what do we have? Ooh, look at this. Oh, well. What are we complaining about is inside. Okay. Hello. We don't have zero link on. No, we don't. What is it complaining about? I have no idea. I'm not going to try to debug this in real time. Okay. Is inside. Why does it not want to tell me what that says? We still have our old code somewhere. Okay. Why do I still have the wrong? Wow, what is? Okay. Well, all right. Today's not my lucky day. I'm not gonna worry about that too much. I'm just actually gonna leave the code there. Okay. So seeing though what is actually happening, right? It's like there's a bunch of just mostly arithmetic, kind of moving that stuff back and forth, and then having the vector do the big work, right? Of inserting and deleting those characters that do all the copying over to get the thing done. So let me come back over here and kind of summarize what good it does and what things it's not so hot at, right? Is that it is easy to move the cursor to wherever you want. That moving it a long distance or a short distance, moving it a little bit or to the beginning to the end, equally easy, right? It's all just resetting some integer variable. It's the insert and delete, right, where this one actually really suffers, right? That based on how many characters, right, follow that cursor, right, you could potentially be moving the entire contents of the buffer. Adding at the end is actually going to be relatively fast. So if you happen to type in order, like you just type your thesis out and never go back to edit anything, then it would be fine adding those characters at the end. But at any point, if you move the cursor back into the mid of the body, somewhere near the front, somewhere in the middle, right, a lot of characters are getting shuffled as you make edits in the middle there. And so what this means is actually that it has good movement, but bad editing as a buffer strategy. That's probably, like given we have these 6 operations we're all interested in, this is probably not the mix that seems to make the most sense for something that's called an editor, right? If the editing operations are the ones that it's sort of weakest on, it has its most debilitating performance, it wouldn't make that good of an editor, right, if that was going to be your behavior. It has one advantage that we're going to see actually kind of like we're going to have to make compromises on, which is it actually uses very little extra space though. That it's using the vector, which potentially might have excess capacity up to twice that, so maybe it's about 2 bytes per char in the very worst case. But it actually has no per character overhead that's already embedded into the data structure from this side. So now I'm just going to go totally somewhere else. So instead of thinking of it as vector, thinking of it as its contiguous block, is that to kind of realize that the editing operations, right, that comes back to the idea like if I were working at the very end of my document, that I can edit there efficiently. that kind of inspires me to think about, well, how is it that I can make it so that the insertion point is somehow in the efficient place, that like the edits that are happening around the insertion point, can I somehow make it to where access to the insertion point is easy? That rather than bearing that in the middle of my vector, if I can expose that to make it accessible easily in the way the code manipulates the internals of the buffer. And so the idea here is to break up the text into two pieces. Things that are to the left of the cursor, things that are to the right. I'm calling those the before and the after. And then organize those so that they're actually inverted from each other to where all the characters that lead up to the cursor are set up to where B is very close, accessible, kind of at the top of, in this case, a stack, and that the things that are farther away are buried further down in the stack in that inaccessible region. And similarly over here, but inverted, that C is the top of this stack, and D and E and things that are farther down there are buried away from me, figuring that the things I really need access to are right next to the cursor, that I'm willing to kind of move those other things farther away to gain that access. And so what this buffer does is it uses two stacks, a before stack, an after stack, and that the operations for moving the data around become transferring things from the before to the after stack. Where is the cursor? How is the cursor represented? Do I need some more data here? Some integer, some... It may be kind of odd to think about, but in fact there is no explicit cursor, right, being stored here. But the cursor is, in this case, right, like modeled by what's on the before stack are all the things to the left of the cursor. What's on the after stack is everything that's following the cursor. So in effect, the cursor is represented as the empty space between these two, where you have, however many characters are on before is actually the index of where the cursor is. So kind of a wacky way of thinking about it, but one that actually has some pretty neat properties in terms of making it run efficiently. So let me show you the code. Let me show you the diagram of it happening. So insert A, B, C, D, E, F, G. And so the operation of inserting a new character into this form of the buffer is pushing something on the before stack. So if I want to move the cursor, let's say I want to move it back one, then I pop the top element off the before and push it onto after. I keep doing that, and it transfers the G to the H, the E, and so on as I back up. Moving forward does that same operation in the inverse. If I want to move forward, I take something off the top of the after and push it on before. So it's kind of shuffling it from one side to the other. Given that these push and pop operations are constant on both implementations of the stack we saw, then that means that our cursor movement is also O of 1. So I can do this, and then when I do deletes, it's actually just popping from the after stack and throwing it away. So also easy to do edits, right, because I'm talking about adding things to before and deleting things from after, both of which can be done very efficiently. The one operation that this guy has trouble with is big cursor movement. If I want to go all the way to the beginning or all the way to the end, then everything's got to go. Right? That if no matter how many things, right, they have to empty out the entire after stack to position the cursor at the end, or empty out the entire before stack to get it all the way over here. So I could sort of talk you through this code, and actually I won't type it just because I actually want to talk about its analysis more than I want to see its code. That each of these actually becomes kind of a one-liner. Insert is push on the before stack. Delete is pop from the after stack. That doing a cursor movement is popping from one and pushing on the other, depending on the direction. And then that same code just with a while loop, like while there's something on the one stack, just keep pushing and popping from one to empty to the other. So very little code to write, right, depending a lot on the stacks abstraction coming through for us, and then making this alternate trade-off where we've managed to get editing suddenly like a lot more efficient, but at the cost of sacrificing one of our other operations. Let's take a look at what that looks like, right? Is suddenly I can do all this insert and delete at the insertion point with very little trouble, and I suddenly made this other operation oddly enough, slow. right? All of a sudden, it's like, if you go back to the beginning of your document, you're in the middle of editing, you're at the bottom, and you say, oh, I want to go back to the beginning. And just, you can imagine how that would feel, actually, as if you were typing. It would actually be the act of going up and clicking up in the top, right, when you're trying to change the insertion, and all of a sudden, you'd see the weight cursor, and you'd be like, why is that taking so long? How could that possibly be, you know, that it's doing this kind of rearrangement? Yet it made editing even on a 1,000,000-character document fast. But that movement, long distances, you know, jumping a couple pages or front to back, suddenly having to do this big transfer behind the scenes. So different, right? So now I had 6 operations. I had 4 fast, 2 slow. Now I have 4 fast, 2 slow. It still might be that actually this is an interesting improvement, though, because we may have decided those are operations that we're willing to tolerate being slower, especially if it made some operation we were more interested in its performance being faster. And that is likely seems like it's moving in the right direction, because editing, right, being the whole purpose, right, behind what we're trying to do is produce a text editor. It seems like that might be a good call. What I'm going to start looking at, and then it's obviously going to be something we're going to talk about next time, is what can the linked list do for us? That both of those are fighting against that contiguous thing, the copying and the shuffling and the inserting. Is there something about that flexibility of the rewiring that can kind of get us out of this, some operations having to be slow because other operations are fast? Question?
On the previous slide?
Yeah.
Why is space used for stack 2n? I mean, both are half.
Yeah. So in this case, right, the idea is that depending on how you're modeling your stacks, if they're modeled as vectors, right, then you're likely to have the before and the after stack both have capacity for everything, even when they're not in use, right? And so it's very likely that either, right, if you have 100 characters, they're either on one stack or the other, but the other one might be kind of harboring the 100 spots for them when they come back. And so, or it could be just be that you have the linked list form where it's actually allocating and deallocating, but it has the overhead of that. So it's likely that no matter which implementation of the stack you have, you probably have about twice the storage that you need because of the 2 sides and the overhead that's kind of coming and going there. And so we will see the linked list, and we'll talk that guy through on Friday. I'll see you then.